Poisson probability distribution, or Poisson, as simple as name it as Poisson distribution, we are still talking about the number of success. Okay, but in binomial, we are talking about success in experiment based on the number of trial. But success in Poisson is based on certain interval or space involved in that particular experiment. Okay, so for the definition of Poisson distribution, so we can easily say the probability distribution for the number of successes X occurs in a specified time interval or space. So if you got the questions, you can see there will be an additional information mentioning about certain space or certain distance or interval. That means it most probably talking about the Poisson distribution. So what are the characteristics of this particular Poisson distribution or Poisson experiment? Okay, so first, the experiment consists of counting the number of occurrences of an event over some interval. So means that for example, if you're talking about 1 kilometer plus highway, so in 1 kilometer plus highway, let's say the experiment is counting the hole. Okay, so how many hole in 1 kilometer plus highway? Let's say in somewhere in northern area. So in that particular case, we are talking about Poisson experiment. You are still counting, okay? Counting the number of hole, and that hole, the number of hole is considered as the number of success. But it happened in certain interval that will be 1 kilometer of plus highway. Okay. Second, the number of the occurrences in one interval must be independent of other intervals. So if you're talking about from 1 kilometer to another kilometer, they are independent of each other. They has nothing to do with each other. Okay, so independent. Number 3, no limit on the number of occurrences in the interval. So there will be no limit. Okay, it can go as long as a huge number as possible, depending on the number of occurrences. We may not know. Okay, and the probability of event occurring is the same for each interval. Means that for one interval of, means that if for 1 kilometer of plus highway with another 1 kilometer of plus highway, the probability of occurring will remain the same. Okay, and finally, the average number of occurrences in an interval is known. So I is here is actually is known. Okay, means that you knew the average number of the occurrence. So that will be the characteristic of Poisson experiment, or what we call as Poisson distribution. Any question, class, for this? Okay, so as usual, we begin with the definition, with the characteristic, and how we can find the, let's say we talk first about the example of Poisson distribution. For example, the first one is number of cars passing a toll booth in 1 hour. So you're talking about the interval is 1 hour. Okay, most of the time the interval will be at the end of the sentence. So in 1 hour, the interval of 1 hour, how many car pass the toll? Okay, so that will be the number of success. No number of defect in a square meter of fabric. You're talking about a fabric. Okay, for maybe cotton fabric, for example. Okay, is there any defect? If there are defects, how many defects? So that will be an example of Poisson distribution. Okay, so the interval is a square metric of fabric, 1 square metric of fabric, and the number of success is number of defect. Third example, number of network error experienced in a day. So in 1 day, okay, in 1 day, how many network error occurred? Okay, in that particular 1 day. So all these are the example of Poisson experiment or Poisson distribution. So the same as what we have in binomial. Okay, so in binomial, we can find the probability of success. Okay, exact probability of success by using NCX P to the power of X Q probability of failure N minus X, where X begin from 0 until any value or N value. Okay, so the same goes to Poisson. You can find exact probability value by using this formula. Okay, so this formula can be applied to find the exact value for X, this particular X. So if you are looking for probability of X less than or equal to certain value of X, then again, you have to come back to your cumulative Poisson distribution. The same goes to binomial. So everything has been simplified for you. You just refer to your binomial or Poisson distribution table. Okay, so if you can find the probability, exact probability value, you can also find the mean. Okay, so this is the mean and this is the variance. Simple. Why? Because if for binomial probability distribution, you have two parameters. That will be, the first parameter is the number of trial. The second parameter is the probability of success. For Poisson distribution, you have only one parameter. Okay, that will be X following Poisson lambda. Okay, so this lambda, okay, will be used to represent the mean of X, that will be lambda, and the variance of X, that will be also lambda. Okay, why lambda? Go back to your example just now, the number of cars passing a toll booth. So there will be one exact value. In 1 hour, there will be how many cars passing through the toll booth. So for the number of defect in 1 square meter of fabric, how many defect? So exact value. That value, all these reflect your lambda. Okay? So Poisson distribution is much simpler compared to binomial. Any questions so far, class? Are you all with me, class? Okay, clear? Eh? Okay, so let us look at the first example. Straightforward to the example without any what we call complicated equations. Okay, consider a Poisson random variable with mean equal to 5. Calculate the following probabilities. Now everything has been clearly defined for you. Poisson random variable with the mean equal to 5. This means you can write down the distribution of your X that will be following Poisson with the number of mean that will be lambda equal to 5. Okay, now write down the Poisson. This is the Poisson distribution. Okay, find Px equal to 0. Oh my goodness, I forgot to put the Poisson table. Let us look at, let me find the Poisson table. Okay, so this is a Poisson table. Similar what you have in binomial, but since in binomial you have the number of trial over here, so this is the number of trial and you have the probability of success. Okay, so this is the number that, okay, I cannot write down, so okay, so this is the number of trial and the probability of success. Now for Poisson, okay, so you can see that in Poisson, if you see this, means that this is a cumulative table, okay, for Poisson. And it reflects the summation. Why? Because we are talking about cumulative value. So cumulative from 0 until number of success X. So let's say in this case, in our example just now, what is the value of the, okay, lambda is equal to 5. So find 5 for lambda. Okay, so you have 5 here. Okay, for lambda equal to 5, you have the number of success from 0 until 16, the most. Why? Because everything maximum 1. So that's why it stopped at 16. Okay, means that you can have further number of successes, but we stop at 16 because the number of successes already got 1. Okay, now what was the question? Find px is equal to 0. So class, if px is equal to 0, this one is exactly taking the value of px less than or equal to 0. So go back to your table just now. So for px less than or equal to 0, so this will be the value. Okay, 0.0067. So this will be 0.0067. Okay, class, straightforward from your table. Now find px is equal to 1. Okay, as what we have done in binomial just now, we are looking for px equal to 1. Okay, so this will be px what, class? Less than or equal to what? Someone? Class?
1.
1 minus px less than or equal to number before 1.
0.
0.
0, yeah. No need to think further. It's directly from your table. So what is to find px is equal to 1? 1 minus 0. Px is equal to 5. Px less than or equal to 5 minus px less than or equal to 4. Directly, straight away, apply that particular concept. So x less than or equal to 1. Here it would be 0.0404. 0.0404 minus less than or equal to 0 is 0.0067. Can someone calculate, please? What is the value?
0.0337.
0.0337. Okay, you can use, since this is a very simple question, is either you use your cumulative table or you can directly use your formula. So if you use your formula, px is equal to 1 equal to exponent negative lambda. Lambda is 5. And then you will have to lambda to the power of x. X is, lambda is 5 to the power of x is 1 divided by 1 x factorial, that would be 1 factorial. So if you calculate this, you will get 0.0337. Okay, if you want to calculate, so please calculate. I think you will get the same value. Okay, what about number 4, sorry. So number 4, you have px greater than or equal to 2. So this will be what? 1 minus px less than or equal to what? Complement of that greater than 2, where 2 is included. So it will be px less than or equal to?
1.
Yes, 1. So 1 minus px less than or equal to 1, that will be 0.0404. So what is the value here?
0.9596.
9596. Right. Okay, so that's how we use our Poisson distribution and find the probability for each of the questions. Okay, so any questions so far, class? Straightforward, right? Now, Poisson is very simple, but then it can be complicated if the condition of the lambda is changed. Means that you are given, let's say for example, just now the example is number of car passing a toll booth in 1 hour. So let's say you are given in 1 hour, let's say x in 1 hour following Poisson is 10. Let's say 100 lah, impossible 10 toll booth we are talking about so many cars. Let's say 250 for example, maybe. That will be in 1 hour. Very busy. Okay, but the question may ask you in within 5 minutes. Okay, so you need to find px less than or equal to 5 for 5 minutes interval. So this is how Poisson will be a bit complicated, where you need to divert or transform your mean for 1 hour to 5 minutes. Okay, so let us look few example if possible. Okay, and before that, so this is how the process of solving Poisson distribution, almost the same as what you have in your Poisson distribution. Okay, so let's say in this case, okay, suppose that the average number of cars arriving in 15-minute period is 10 cars. Find the probability that exactly 5 arrivals in 15 minutes. So if you can see, the interval still the same. Fine, it will be easy for you. Okay, so in this case, x will be what? What is the definition of x in this particular case? The number of success. What is the number of success defined in this example 6?
Minit
The the the
15.
the full terms. That will be the number of cars. Number of cars, because we are talking about the success, right? The success will be the number of cars arrive. Okay, in 15 minutes time. So this will be your definition of your random variable x. And this x following Poisson. Why? Because we are talking about an interval of 15 minutes period of time. So Poisson with mean equal to how many? 10 cars. Okay, so within 15 minutes, 10 cars arrive. Okay, is it correct? Suppose that the average is 10 cars. Yes. Find the probability exactly 5 arrive. Px exactly 5. Okay, so let's say we go back to lambda equal to 10. So go for lambda equal to 10. So here we got 10. Okay, we got 10 here. And then we are looking for x equal to 5. So we know that equal to 5 is either you use directly your formula. If let's say we are using our cumulative table, this will be what class? Px less than or equal to what? Class? Less than or equal to what? Hello, are you all with me?
5.
Yes, 5 minus Px less than or equal to?
4.
Yes, directly from the table. So we can see less than or equal to 5 is 0.0671. 0.0671 minus 4, 0.0293. 0.0293. Can someone calculate, class?
Um, 0.0378.
Okay, right. Okay, and if you use your formula, Px equal to 5, this will be e to the power of negative 5, negative 10. 10, lambda. Negative 10. 10 to the power of 5, 5 factorial. Okay, I believe it will go back to 0.0378. Now, let us look at one example where the interval has been changed and you need to alter or transform the mean value. Okay, so let us look at this particular example. Okay, the average number of traffic accident on a certain section of highway is 2 per week. Okay, this is one example. Okay, so 2 accident per week means that the mean is 2 for 1 week. So in this case, X will be, X is what? Number of what? Class? Number of?
Traffic accident.
Yes, traffic accident. On a certain section, if to be longer lah, on certain section of highway, if not just take the in 1 week, in per week, in 1 week. Okay, X is the number of traffic accident on certain highway in 1 week. And we know that X is following Poisson with 2 number of accident in 1 week. Okay, so the first question, find the probability no accident. So no accident is what? Px is equal to what? No accident.
0.
Yes, X equal to 0. So for lambda equal to 2, go for lambda equal to 2. Okay, lambda equal to 2, X is equal to 0. Okay, 1353. Px less than or equal to 0, 0 point, what was that just now? Uh, 1353. So this one in 1 week. Now the second question, find the probability of 3 accident on this section of highway during 2-week period. Now you are talking, the question asks you in within 2 weeks period. So we know that this is for 1 week period, 1 week. So if we are talking about 2-week period, it become what? In 1 week, 2 accident. So for 2 weeks, that will be
4.
4. Yes, 4 for 2 weeks. Okay, so the second question, find probability 3 accidents. So exactly 3, you can use the formula or you can use the cumulative table. Let's say we use the cumulative table. So Px less than or equal to what? Less than or equal to what?
3.
3. Okay, minus Px less than or equal to?
2.
Yes, 2. So look for, now, just now we look for lambda equal to 2. Now we look for lambda equal to 4. So it will be referring to different table. Lambda equal to 4. Okay, lambda equal to 4. Look for 3 accident. So that will be less than or equal to 0.4335. 0.4335 minus why am I x is equal to 0? X is equal to 0. I'm following the correct, right? For lambda equal to 2, X equal to 0. Let me check again. Lambda equal to 2, X equal to 0, 1353. Okay, 1353, correct, right? Then for lambda equal to 4, 2 is 2 per week. Betul? This one correct, this one correct. X is equal to 3, 3 minus 2, go for lambda equal to 4. 3 minus 2, 4, 3, 3, 5, 0.2381. 0.2381. 0.2381. What's your answer, class here? Class?
0.1954.
54. Okay. I hope it's correct. Okay. So that's how you solve. Okay. So it's not difficult, but you have to bear in mind, look for specific interval that is being asked in the questions. Okay, if we the tedious part of Poisson is that part only. The rest of the part is just simple. If let's say you need to find the mean and variance for this particular x, okay, what is the mean of x here? What is the mean? The average number of accidents in 1 week? It
2.
will be no. Yeah, 2. Oh, sorry, correct. Okay, what is the variance for x?
2.
2, correct. What is the standard deviation of x? Square root of 2. Okay, as simple as that. Okay, so that will be how to find probability for Poisson distribution. Any questions so far, class? Okay, let us choose one question. One question that will be a bit question 1. Okay, question 1. I think question 1 is kind of interesting question to be discussed. The rest of the question I want you to try to solve it. Okay. Now, phone calls received at the rate of 48 per hour means that in within 1 hour, okay, the number of phone call received is 48 calls at the reservation desk for regional airways. Okay, find the probability of receiving 3 calls in 5 minutes interval. Find the probability of receiving exactly 10 calls in 15 minutes interval. So see, the interval change every time it being asked in terms of the probability value. Now, let's begin with the initial part that will be defining what is your x in this case. Okay, what is your x in this case, class? Number of what?
1.
No. Number, the definition first. The number of what? The number of,
Phone call.
yes, phone calls received at the reservation desk in 1 hour. Okay, we know that in 1 hour, the number of phone calls is 48. Okay, so this one is for 1 hour. Now, the question asks, find the probability of receiving 3 calls. But in this case, you are being asked about 5 minutes time. How to find the interval for 5 minutes? If for 1 hour, you will receive 48 calls, what about in 5 minutes? How many calls would you have? Okay, so you have to make something with the number of calls received within 1 hour. So in this case, if 1 hour is 48, so how many for 5 minutes? So simply 48 over 60 minutes, okay, times the number of minutes that we are looking for is 5 minutes. Okay. So when we divide by 60 minutes means that we can find for every 1 minute how many? Since we are looking for 5 minutes, so we multiply by 5. So what is the value here, class? 48 divide by 60 multiply by 5. What's the value, class?
4.
4. Okay, means that the distribution, the following Poisson for 5 minutes will be 4. Sorry, wrongly written. Okay, 4, that will be for 5 minutes. Okay, so we have another one for 15 minutes. For 15 minutes, what about for 15 minutes? How many? 4 multiplied by 5 minutes for 15 minutes. Dapat berapa?
Twelve.
Yes, 12. Okay, so this one for 15 minutes. Okay, so let's solve for the first question. Px is equal to 3. Then we can use Px less than or equal to 3 minus Px less than or equal to 2. Look for lambda equal to 4. This one, lambda equal to 4, 3 minus 2. Lambda equal to 4, 3 minus 2. 0.4335. Okay, minus 0.2381. Right? So 0.4335 minus 0.2381. Okay, so what's the value here, class? 0.
1969.
19605. 4335 minus 0.2381. 19 what was that? 54. Right? Okay. So finish for this one following X Poisson 4. Okay. For B, X Poisson 12. Okay. So PX receiving exactly 10 calls. 10 calls. So this will be Px less than or equal to 10 minus Px less than or equal to 9. So lambda 12. Look for lambda 12. Lambda 12. And we are looking for 10 minus 9. 10 minus 9. 10 is 0.3472 minus 0.2424. Okay, so go back to your process. So this will be 0.3472 minus 0.2424. What's the value here, class?
Oh, 1048.
Okay, 1048. So that's one example of how we can change the interval in order to find the probability value when the interval has been changed. Okay, so that would be one example. Okay, any questions so far, class? Any questions so far? Do you want to do another question or let us move to the last part of my discussion for today's lecture. Any question that you want me to discuss? Poisson approximation. So there are another 2 questions here. I think you can try on your own, the rest of the questions, okay? If you have any question, you can ask me, okay? Now, the last part before we can move on Monday to the normal probability distribution, that will be the last distribution that we are going to discuss, is the Poisson approximation of binomial probabilities, okay? So we have discussed about binomial. We know what will be the characteristic of what we call binomial experiment. We can know how to find the exact value, probability exact value for binomial, and the same goes to Poisson probability distribution. Now, there will be certain cases where you can do the approximation, okay? By having a binomial problem, binomial equations, you can solve using Poisson approximation. And how this become possible, okay? So let us look at the few of the concept how this become possible, okay? So the Poisson distribution is suitable as an approximation of binomial probabilities when n is large and p is small. Okay, so that will be the first definition that you need to understand. Okay, you can do the approximation using the the Poisson to solve for the binomial equations. Okay, and the approximation can be made when n greater than 30 and either np or nq less than 5. Means that here, class. Now, when do I know that I need to do the approximation? When to use the approximation of from the binomial equation, you solve using Poisson equation. Okay, so the first condition is when n is greater than or equal to 30. Seems very small, right? The first condition, if you can see, if the binomial equation, the number of trial is 30 and above, then you should have in mind this could be done using the approximation. But based on the second, what we call characteristic. Okay, the word here, remember the word here n. So means that there will be 2 characteristics that need to be fulfilled. The first one, n greater than or equal to 30. The second one, either of this. Either one. Either this one or this one. The words or. Okay, so means that the first is n greater than or equal to 30 and the second one is np less than 5 or either one. If np less than 5 clear, then go ahead. You can do the approximation. If let's say np is not fulfilled, check for nq. If nq is less than 5, then you can still use the approximation concept. So it's either one, okay? Either of the 2 condition. Now that will be the what we call the scenario, how you can do the approximation from binomial to Poisson. And of course, when we do the approximation, the original probability distribution is following binomial, okay, with n number of trial and probability of success p. When you approximate, how does the probability distribution looks like? So x will be following Poisson with lambda is equal to n multiplied by p. So that will be your lambda. Okay, any questions so far, class? Okay, is everyone okay, class?
Okay, Doctor.
Okay. Really sorry, we don't have any rest. But the video afterwards, I will try my best to split into 3 videos, so that it will be easier for you to look to watch the video. Now, let us look at the first example. Straightforward example without no context equation or problems involved in that particular equation. Given that x is following binomial with number of trial 1000 and the probability of success is 0.004. Very large number of success but very small probability of very large number of trial but very small probability of success. So in this case, we need to check. So in order to check, it must be fulfilling the two conditions that we have just discussed. Okay, the first one just now. Okay, the first one is n is equal, in this case is 1000. Yes, it's greater than 30. Checked. Okay. Second, np. There is 1000 multiplied with 0.004. Okay, you will get 4. In this case, n is less than, np is less than 5. Checked. Those two conditions fulfilled, then we can do the approximation. So, originally, x following binomial with 1000 and 0.04, it become x following Poisson with 4 number of mean. Okay, now you need to find what is px less than equal to 7, equal to 7. So in this case, px less than or equal to 7 minus px less than or equal to 6. So for lambda equal to 4, go for 7 minus 6. Lambda equal to 4, 7 minus 6. 7 minus 6. 9489. Okay, so this becomes 0.9489 minus 0.8893. So what's the value here, class? 8893. Is it correct? 8893, yes. What's the value here, class?
0.0596.
Yes, 5956. 956, right? 596 or 956? This is correct, right? Okay. Okay, then B
596.
596. Oh, 596, huh? 596. Okay. Now, what about px less than 9? This is what? Directly. 9 is not included. So we are looking at the cumulative table. So it become what? P,
Less than 8.
yes, less than 8. Directly from your table, where lambda is equal to 4, less than or equal to 8, 0.9786. 9786. Okay. So high likely that less than 9 successes occur for this particular experiment. Okay, high likely. A, very small. Less likely that exactly 7 success occur for this particular experiment. Okay, any questions so far, class? Let us try one example here. You have extra exercise. 2, 4, 30, 10, 12. Okay, let us try this one. Okay, let me give you 5 minutes and then we discuss the answer, then we finish our class. For this one, class. Of course, you don't have your table. I believe some of you may have got your table, right? So let's do it together and then you do the calculation, okay? Let's say in this case, what is X here, class? Last month, ABC sold 1,000 new watches. Past experience indicates that the probability that a new watch will need repair during its warranty period is 0.002. Compute the probability that at least 5 watches will need to warranty work. So let us define what is X here. What is X? Number of success. This is binomial, yeah? Since we have a number of trial and probability of success. In this case, the success is probability of the watch need to be repaired. So X will be what? Number of what? Number of what? Watches, right? Number of watches required repair during warranty period. And we know X following binomial with number of trial 1,000 and probability of success that will be need a number of watches that require repair is 0.002. Okay, check for the condition. Okay, so in this case, condition first, n equal to 1,000 greater than 30. Second, np 1,000 multiply 0.002 will be what? 2, right? Less than 5. Check. Okay, so in this case, X approximate to Poisson with 2, the number of mean 2. Okay, now first P at least 5. Px what? Greater than or less than? At least.
Greater than.
Greater than or equal to 5 watches. Need to warranty work. So this will be 1 minus Px less than or equal to what?
4.
4. So 1 minus, for lambda equal to 2, look for less than or equal to 4. 2 less than or equal to 4. 0.9473. 9473. Is it the answer here? Is it correct? 0.0527. Macam tak je. Yeah. Correct. Is it correct? Is it correct, class?
Yes, Doctor.
Okay. Done. 2 Roman. At most 3 watches. So Px what? Greater than or less than?
Less than 2.
Less
Less
than.
than
Less
or
than
equal
or
to
equal.
3. So directly from table, lambda 2 x less than or equal to 3. 2 less than or equal to 3, 8571. 8571. Right. Less than 7 watches will need warranty work. P Roman less than 7. Px less than 7. So it will be what? Px less than or equal to what? Last, come on. Last question. Less than 7. So it will be less than or equal to
6.
6. Yes. Seems you still very slow in terms of identifying what will be the number. Okay. So less than or equal to 6 for lambda equal to 2. 6. So 9955. 9955. pi 5. Right. Okay, so that's how we do such equations. For originally you are being given in terms of binomial, and since the condition of approximating to Poisson is fulfilled, you can solve them using Poisson. But can you still use binomial to solve, class? Can you still use binomial to solve, class?
Yes.
Yes. But what will be the
Yes.
hard the hardship or the difficult part that you need to refer to? If you are using binomial for this particular equation, if you are still using binomial, what will be the most difficult part that you need to do? Can someone answer my question before we leave? If we are
The
still using,
1000.
yes, we need a cumulative table of binomial that reach 1000 trial, and we know that our binomial table, for example in our case, we have at most 30 trials only, not up to 50. Okay, and 30 trial for 0.5 probability of success. So because of the limitation of the binomial table, sometimes the approximation will be very much easy for you to use in order to solve the given equations. Okay, class? So, by today's class, we have seen how we can solve if we have binomial problem, the probability of success is greater than 0.5. We can use the complement of the probability to solve them. Second, we can see how the Poisson probability distribution can be solved. Okay, and the different concept as opposed to what you have in binomial, and finally how we can solve binomial problem using Poisson approximation. Okay, class. So far, before we leave, do you have any questions for what we have discussed today? Any question?